So, all right, thank you, Professor Mahesh, for the introduction. So, good morning, everyone. My name is Shinzi. So, it is my pleasure to be the first speaker to present at the conference. So, today I'm excited to share with you on how you could update your 5G vRAN. So, this piece of work was done more than a year and a half ago, together with Anuj Kalyal when he was at Microsoft. So, let us begin. So, over the years, the radio access network has undergone a series of major transformation. So traditionally, it was built using proprietary tightly integrated hardware. So usually we call them as baseband units. And today, it has evolved into a virtualized and disaggregated architecture. So by virtualization here, now today the RAN runs on commodity servers using CPUs or GPUs. And by disaggregation, so the BBU, or the baseband unit, is now split into multiple components. One of them is the centralized unit, and the other one, which is the distributed unit. We will call it the CU and DU later on. So since the RAN is now softwareized, so software updates are essential part of day-to-day operations. So this is just like any cloud application. So eventually, there will be bug fixes, there will be security patches, and also there will be feature updates that needs to be rolled out from time to time. Today, the current approach is to do a simple stop and replace. Basically, we stop the current running version, and then we submit a new one. Just like this. The issue of such an approach is that during the update, the network itself is disrupted for a prolonged period of time. So later I will show that this can be up to more than tens of seconds. So in this work, the question that we try to answer is that, can we actually minimize this disruption and make software updates for vRAN a seamless process? So before we dive deeper, so let us look at some of the prior works on vRAN software updates. So 2 years ago, also presented in this conference by Jarong and the other authors. So they presented Atlas. So in Atlas, so what was presented was that how they did DU updates is that they require a spare server to spin up the new version, and then they use a programmable switch to redirect the traffic from the old DU to the new DU to complete the update. But then, if you look at today's dominant vRAN deployment model, so which is what we call a distributed RAN architecture. So in a DRAN setup, in a distributed RAN setup, so there's only usually one server at the south side, just enough to serve the radios at the site. So given this deployment model, what was presented by Atlas does not fit. I mean, it's not a suitable one. So that is for the DU. And how about the CU? So as of now, so there's no published work in this domain as well. Now we have a better sense of how the current state of things looks like. So then we'll then look into the individual challenges of updating the DU and CU individually. So first, let us talk about the DU. So what is the challenge? So the DU itself, it handles the baseband processing and also the MAC scheduling. So it is a real-time sensitive process. If you try to on the same server, if you try to spin up another instance side by side with the old instance to do the update, what will happen is that the old instance, the old DU and the new DU, they will be competing for CPU resources. And when that happens, both will miss their real-time processing deadlines, and eventually both of them will crash. So that is not a good option. So if you look at the second option, which is what is currently being done, so if we shut down the old one, and then we start up the new one, so the downtime, based on our measurement, at least in our setup, the downtime is more than 25 seconds, and it can be even longer. So the reason behind this long downtime is two. Number one, when you shut down the old DU, it takes some time to deinitialize to release the resources. And the second, when you start up the new DU, it takes time to pre-allocate the memory, start up the network interface, and also wait for the system frame number to realign. So this is about the challenges relating to DU updates. And next, if you look at CU updates, how about the CU? For the CU, it is not a real-time process, but then the CU itself is the aggregation point of the RAN. So if you remember the diagram that I showed earlier, So a CU, it can be associated to multiple DU, basically like a tree. So it can be hundreds of DU being associated to a common CU. Can we try to spin up a new CU alongside the new CU? So unfortunately, no, because the DU are statefully associated to each of the CU. If you want to change the association, we have to restart the DU. This is also not a good option. So how about we shut down the CU and we start a new CU? Well, technically you can. So the downtime is not as much. It's about 7 to 8 seconds. But then, since the CU is the aggregation point of the network, if you queue up the CU, basically your whole network goes down. So when the new CU comes back up and all the DU reconnects and all our phones try to reconnect to the network, so basically this usually would happen synchronously, and this will cause a signaling storm, which will eventually cause the downtime to be much longer. So now you have a sense of the challenges involved in updating the RAN. So therefore, to address them, we present SwapRAN. SwapRAN is the first live update system that covers both the CU and the DU. So as an overview, so for DU updates, it involves two techniques. Number one, we introduce techniques that allows us to safely overlap the old DU and the new DU so that the new DU can start up in the background while not interrupting with the real-time process of the new DU. And number two, when the new DU is ready to take over, we repurpose the embedded switch on modern interface cards, so to reroute traffic to the new DU. And secondly, for CU updates, we introduce a mid-hop proxy to preserve the stateful connection during CU updates. And to prevent signaling storms, we use our proxy to control the pace of the update. In this talk, I'll only focus more on CU updates, and more details on DU updates can be found in the paper. So as I mentioned just now, to mask the CU update process from the underlying DUs, so we introduce a proxy. So basically, this is very similar to how reverse proxy works in data centers, how they mask the application from the end user. So now the DU is unaware of the CU being replaced, being updated in the background. But then there is still a problem. Because the new CU basically is fresh, it doesn't have any states of the UE, and we cannot just, the proxy cannot just simply redirect traffic from the old CU to the new CU because it would just cause all the UEs to lose their connection. So how can we actually solve this? When developing SwapRAN, so we tried two approaches. Number one, we could try to issue a handover command to the UE, basically from the CU, to force the UE to move from the old CU to the new CU. Or number two, we could force the UE to reestablish a new radio connection. So both of this approach, they do work, but then there's a practicality concern. So since both of these operations, basically you try to trigger a handover or basically force the UE to reestablish a new connection, these are high-layer radio level controls. Basically, you need the XApp, basically you need the rig in order to do this. But then the software update process lives in the orchestration domain. So basically now you need the radio management people to work together with the orchestration domain people. So this would have some challenges in order to get this workable in practice. So based on this, is there a simpler, more elegant way for us to force all the UE associated to the old CU to move to the new CU? So our approach here is that instead of dealing with the individual UEs one by one, we deal directly with the DUs. We do so by doing soft resetting the DUs. We do so by reusing standardized reset messages, and we use our proxy that we introduced just now to generate them. What happens is that when we soft reset the DU, so the DU would lose all its states, and eventually all our user devices would lose connection to the DU, and it would immediately try to reconnect to the network. So this is how we force the user devices to reconnect and eventually move to the new CU. And second part is that how can we actually prevent signaling storms? So as I said, so by using our proxy, we can generate the reset messages one by one for each DU in a gradual manner. So this allows us to manage the signaling load as well. As an illustration, so we have the old CU here, and we spin up the new CU, what happens is that the F1, our mid-hop proxy will generate a reset messages to each of the DU, and then all the user devices would try to reconnect to the network, and they would be reassociated to the new CU. And this process happens in a gradual manner. I'll just quickly go through this. Right. So that concludes CU updates. So moving on, so we'll talk about the evaluation setup that we tried to test SwapRAN on. So when this work was done, so it was evaluated on, so for DU updates, it was evaluated on a commercial 5G testbed at Microsoft Redmond. And for CU updates, it was evaluated on our 5G testbed at NUS. Later on, we have also implemented a version of SwapRAN for especially the DU update part on the open source open air interface on our NUS testbed as well. As a key result, so we use a single UE, and by using IPv3 traffic, by generating IPv3 traffic, so we then compare them with the default Kubernetes update strategies. So as you can see, without SwapRAN, so basically without our solution, the downtimes are up to 25 seconds and 7 seconds for DU and CU updates respectively. And when using SwapRAN, the downtime are as low as 1 to 2 seconds. So as indicated by the purple lines. A 1 to 2 second downtime is comparable to any typical intermittent network connection hiccups. For example, when you are walking past through a tunnel and you briefly lose connection. So basically to the user, they don't feel anything. So this is eventually what SwapRAN is able to achieve. We also have more results on scenarios using multiple UEs, multiple DUs, and even also using a real application to demonstrate that, let's say during a video conference, when the software update processes happens, the user does not really feel that there was an update in the background. So that concludes my talk. And we will also be demonstrating SwapRAN later throughout the conference. So in the demo session this Wednesday, and also in the OpenAI RAN workshop later this Saturday. So we hope to see you there. And that concludes my talk. Thank you very much for your time.
We have time for a couple of questions. Anyone?
Thank you for the great talk. This is Shiming from Hong Kong PolyU. And I have a simple question that in the operational run, how often do we really need to update the software?
Because now everything is in software. So usually bug fixes, security patches, they come more often than we expect. So let's say if we take the open source open air interface, for example, there would be major releases, let's say every 6 months. Or let's say if you're doing nightly releases, it can be even more frequent. So it is, at least it is something that we need to tackle.
Oh, thank you.
Any more questions? Let me ask you a couple. So you presented mainly about the software update side of it, but could you use SwapRAN system in the context of failures, as in crashes, like DU crash or CU crash, and recovering from that?
No, I think it's a different implement. I think the context itself is different. So what we do here is that because this is a planned operation, so we know that this will happen, so that we can roll things out in advance in order to do the migration seamlessly. But in the case of a failure, there's something that we cannot predict, and the optimization or basically techniques that we introduce here do not apply in that context.
Okay.
But we do have some optimizations that allow the DU to to start up much faster than a typical DU would do. So perhaps some of those optimizations may apply.
Okay, I think we have a question there.
Thank you for your interesting presentation. I'm Sohei from KDDI, Japanese operator. So actually, we do the software update every day. My question is the downtime. In the commercial network, we need more downtime. That is, you said the downtime for DU is 7 or 30 seconds, but actually we need more time. So So in such case, in the case we need more time to update the software, and if we use your method, what is the difference between the result you showed here and in the case of the longer update time?
I'm not quite sure. So if I understand your question correctly, so basically what is the difference of using sovereign and without, right? Basically in the background, in terms of the infrastructure side of things. Okay. So maybe we can talk more about this. So I'll just give a short answer for now. So basically what the key of using sovereign is that we assume a Kubernetes setup. So I believe in the operator you're using Kubernetes. And basically we introduce additional hooks and some software libraries that Kubernetes can dynamically load into the Kubernetes together with the RAN software. So from the operator's point of view, it does not change much of your operation. You just need to add something. Okay, we can talk more after this.
Okay, thanks for your wonderful presentation. And this is Johnny from PolyU. And I noticed in your results that there is a huge fluctuation for your throughput when you. Oh, thank you. There is a fluctuation for your throughput, and will it cause some safety problems, like make the network more vulnerable to be attacked? Thank you.
So for this fluctuation, so it is something to do with IPEP or something to do with TCP. So basically when the connection resumes, there's a TCP tries to retransmit a lot of things, and eventually that's why you see this sudden surge in traffic. So this has, I believe this has nothing to do with any security vulnerabilities and such.
Okay, thank
All
you.
right, thank you. Thank you for the question.